3, Math 2, Math 1, whatever. So instead, I decided one that you all are terrible at, which is another mathematics, which is the mathematics of scheduling. You're all terrible at that because I'll sit here at 11:30 when class begins, and we still won't start until about 11:50. So you're all terrible at scheduling. So what we're going to do is go into our last module, that is the mathematics of scheduling. These are all the essential questions from section, whatever, 8.2, 8.1, and they're all here. They're a little jumbled up, but I want to start off on section 8.2. And so our question is, how is a digraph different from a graph? And we'll talk about what a digraph is in a minute. Word wall, these are words that I will use that you should be kind of familiar with. Adjacent is one that I know you should be familiar with at this point. You might not know arc set or all of these, but we will talk about all of them by the end of this module, end of this chapter. So let's jump right into it in digraphs. And so again, this is everything. This is all of my work. I'm going to try to grab here so I can zoom out just a touch. That way we can all see. And you should have all of the notes up at the top. And so you can just copy and go through at your own pace, submit whenever you're ready. We have started the recording, correct? Mm-hmm. Perfect. So the first thing here on section 8.2 is he or she loves me, he or she loves me not. You probably heard of this, right? He loves me not. So if we have a boy, B, and a girl, G, what are different ways that these two people might like each other? Well, boy like girl only, girl like boy only, boy don't like girl, each other don't, they both like each other, they don't like each other, whatever. So let's represent this interest or lack thereof in a graph, right? So let B be the boy, G be the girl. So if I draw an arrow from B to G, what does that mean?
Boy likes girl.
Boy likes girl. If I draw an arrow from G to B,
Girl likes boy.
girl likes boy. But the feelings aren't reciprocated in these two situations, right?
Friend zone.
If there's a boy and a girl and there's no line between them, guess what?
They don't like each other.
Boy don't like girl, girl don't like boy. Okay? But if there's these two arrows, guess what? They like each other. That's a match. That's a match, people. Okay. These are graphs and examples of what we call directed graphs or a digraph. That's an excellent observation, even though I'm not going to use that specific example. All the dating apps out there probably use something like this, right? Can you believe that an app that people use on a day-to-day basis comes back and uses mathematical concepts? Amazing.
Well, I mean, you gotta find some way. You gotta use math to find a match.
Exactly. Analytics, people.
And that's why that dude's making.
I don't know that.
That's a good thing. So these different graphs are examples of what we call a directed graph or a digraph. Why is it called a digraph?
Because it's direct.
Because you're seeing a direction and that line represents something formed, right? Some idea here in the digraph, right? So a directed graph or a digraph is a graph in which the edges have directions associated with them. For example, the interest of one person was our direction association here in this problem, right? Direction association. Direction association.
Oh, would you please remind us that we are working on 8.2 notes right now?
We are working on 8.2 notes.
Because Mr. Lanky is not.
I don't even want to walk back there. What's he asking about?
He didn't know which notes we were working on, and I said, and he didn't. He missed your introduction that we're doing 8.2 first before 8.1.
Oh yeah, right here. You see this? This is what we're talking about. 8.2 directed graphs and diagrams. Top of the paper, highlighting. The first thing on your student notes. Okay, So some key terms about digraphs. These are some things that you're going to want to keep, in your knowledge bank. Not a ton here. Some of them you've heard before, hopefully heard before. If not, that's okay. It's not the end of the world. Arcs. Arcs are directed edges of the digraph, or the arrows, right? The arc is again, directed edges of the digraph, the arrows that we have. So that first bullet there says direction equals the starting vertex to an ending vertex. That is the direction. Draw an arrow where you start to where you end. Self-explanatory. So if I had X, Y, you would draw an arrow. If it's written this way, you draw an arrow from X to Y. This is not back where we talked graph theory and the directions of, or the mathematics of travel, right? Where X, Y, and YX can be the same thing in an edge. Technically it can, but when I talk about a digraph, the direction matters. So if I put X, Y, that tells me I start at X and go to Y in my vertex. And conversely, if I write it as YX, I start at Y and draw an arrow to X. So how would we write each of these up here off to the side, right? This is AB. Why? Because I start at A and I draw an arrow to B. You might want to write that down if you have not already. Yeah, you want to write down the part above it, right? Because yours is blank, you're going to write these in between. So see how this goes from C to B, not B to C. So it would be written as CB.
So the way the arrow's going is like, so C to B, you write C first.
Yes. And since B goes down to D, we would write that BD. If I look over here at A goes to D, AD. A has another one pointing to it, but it's pointing to it, so it starts at E and goes up to A. E, A,
Again.
Now, from D to E, again, across. From D to C, DC, comics. There we go. I think that's all of them. And that is just you defining the arcs. That is you defining the arcs. So what do you think an arc set is? Oh, wait, it's the list of all the arcs. That's what a set is. A set is when you list everything that's there. Let's see, next thing over here. An incidence is a relationship of vertices, direction of arcs, to or from. A incident to B, A to B. Where are you going to? Start, incident to end. You with me? E, incident from D. DE, why? Where are you from? It's all about the language here. End, incident, from, start. So if I said incident to, you read it like the way you would list it, A to B. If I said incident from, it's backwards. Incident to, the same way. Incident from, backwards. Might be something that you decide you need to, I don't know, star. Why would I star that? It's not that important. Well, it's something that is easily forgotten. Something that is easily forgotten. Okay. So I'm going to trash that, close this, and move on down. Adjacent arcs. An adjacent arc, starting vertex of one arc is the ending vertex of another. So first letter arc equals second letter of another. Here's some examples of adjacent arcs. CB and BD. Why? Ended with B, started with B. DE, EA. Why? Ended with E, started with E. Visual representations of this. CB, BD. AB, BD. These are adjacent arcs. EA, AD. DE, EA. Why? I start or I end the first one with the letter and start the next one with that said letter. Make sense? All right, a path is a sequence of adjacent arcs between initial starting vertex and finding ending vertex, and no arc appears more than once. So this is just like a path back from what we talked about before, only now you have direction. So instead of you finding a Euler circuit, right, now instead of that, you have a direction, and a path is a sequence of these arcs that go from a starting point to an ending point, and finding the end vertex. No arcs appear more than once, just like before. So I could have started here, and I could have went from A to D, D to E, E to A to B. You might think, hey, you already did A. It's not the arc. The vertex can be hit more than once. The arc itself cannot, right? And this is actually a circuit. Boom, 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 boom. Well, not a circuit. It's a path.
Can't go back to A.
Because we cannot go back to A. So each one can hit, but that would be a path. Just like what we had a path from before. List of vertices or arcs in order equal the path. I would put them in arcs just because it's nice to see that. But you could put them as vertices. Either way is accepted. You should be able to determine between the two. You should know what a circuit in a graph is, right? Circuit in a graph, just like what we talked about in our previous unit. Starts and ends at the same vertex. Same thing we talked about back in our lessons on Euler circuits and Euler paths. So a cycle, this puts path starts and ends at the same vertex. Moving on. Continuing our work here with directed graphs. The degree of a graph, we have not like odd and even degrees, like we talked about with the vertices and how many edges meet. The degree in a graph, we've got out degree of a vertex. This is the number of arcs in which the vertex is the starting vertex of, outgoing. Where does it begin and how many does it go out to? And then end degree, how many arcs end at that vertex coming in. So the total degrees equal the total end degrees, which is the total number of edges. So how many out degrees does A have?
2.
2. It has 1 end degree, right? So 2 out degrees, 1 end degree. D, 2 end degrees, 2 out degrees. B has 2 end degrees, 1 out degree. So if I was to come down here again, I believe this is actually plus and got mixed up. So total of out degrees plus the total of end degrees equal the total number of edges. Again, that should be easy. That's something we just did back in our previous unit. So take that knowledge back from the mathematics of graph theory and traveling to put that in perspective here. Any questions so far? Okay. When
Does
does
this little packet like all the notes?
correct?
Yeah.
Okay, so we're just gonna stop at the 2.
Correct. The next thing you guys had was,
Examples of key terms.
okay, examples of key terms here. So example number 1, consider the digraph right, to the right. A is an incident to B, D, and C. Why? Look at your arrows. A, Incident 2 here, which you can't really see that being D, but it is. A to D, A to B, and the double, right, they both like each other. That's also called a multiple edge, if you remember, right, A to C. So for you, it says A is incident from what? A is incident from C and E. Those are the only ones that have arrows pointing to A. Incident from points to, incident 2 points away. Or starts at. Now the next question, I'm going a little fast, so I need to slow down. Okay. Find the in degree and out degree of each vertex. So if I start at A, in degree, how many are coming in? 1, 2. Right? Out degree, how many are going away from it? 1, 2, 3. I put 2/3, but it's 2, 3. 2 in degree, 3 out degree. B has 1 in degree and 1 out degree. C has 1 out degree, 1 in degree, and 3, 1, 2, 3 out degrees.
Do you always put the in degree part?
It's just because of the way it was questioned. Yeah, it's just because of the question. I could have flipped it around, and that's just kind of me organizing the numbers and not having to write it, a bunch. D. D's popular. Everybody goes to D, right? All in degrees. Does not go away from it all. E is 1 in, 2 out. Questions on that? So, the next one says find a path from A to D. From A means we got to go away to begin with, and it doesn't say how many, I have to take, so I could go from A to C and C to D. Why would that be nice? Well, that's only 2. Is there one that's quicker than 2? Sure, A to D. That's a 1. That's the shortest distance between the 2, A to D, with the least amount of stops. We could have also went from A to B, B to D. And you can look at the way that these are stated. A to D, A, B, D, A, C, D. I could go A to C, C to D, D to E. I don't know why you do that, but you just hit, more than one. You could go A to C, C to E, E back to A, right? A back to C, and then C to D. We could go AC, CA, AD. You don't have to do all of these. I'm just showing you a bunch of different representations. Do any cycles exist? If so, where? Remember that a cycle is like a circuit, cycle circuit. So, what I would do is the same thing that we learned before. B is a degree of 2. A is a degree of 1, 2, 3, 4, 5. That's interesting. C is a degree of 1, 2, 3, 4. E, 3, and D, 4. So there's definitely a path. However, there's not a circuit that hits all of them. It doesn't ask for a Euler circuit. It just says, is there a circuit? There are. We can go C to E, E to A to C. That's a circuit. It's just not hitting everything, right? We could go A to C, C to A. That's a circuit. We're just not hitting everything. Okay? Does that make sense? Or a cycle. Cycle, circuit, same thing. All right. Example 2, consider the digraph of the arc set. So, without a graph, what is the out degree of V and Z? Without a graph, if I give you the arc set of a diagram, what is the out degree of V and Z? Well, how many times is it listed first?
The is twice.
Right, 1, 2. Z is listed 1, 2. So the out degree of both of them is 2. I don't need a graph for that. If they give me the arc set, I can just look at out degree, how many times is it listed first? Which means that if I look at in degree, how many times is it listed last or second? Well, V is listed last none, and Z is listed last once, twice, 3 times.
I think it's easier like that.
Then to have the graph? Well, you have to have it listed out like that, but yeah, they're both pretty easy.
I think this one, they just think we want.
Well, I think it all just kind of falls into place since you've already done something similar to this. Applications of digraphs. When I say applications, I think I gave you a question like this back in our last module, right? I said, what are the applications of this thing? And you had to come up with it. Well, here are 4 applications of digraphs. Traffic flow. Arcs can represent two-way or one-way streets, right? Traffic flow. People would do a digraph to represent that. Tournaments. Vertices would be the teams, the arcs, the outcome of the match. Some of you have seen that before, right? You've seen a tournament list, and generally when you see a tournament, it's the same bracket every time. But that represents, right, a diagram. It's nice and neat, and everybody's seen it before. Telephone traffic, which you've seen those commercials from Sprint, well, not Sprint anymore, T-Mobile. You've seen it from AT&T and Verizon, where they're like drawing lines from a tower to other places, right? That's phone traffic, okay? When we say phone traffic, if any of you guys, here's an example, if anybody decided that they wanted to go to Tanglewood Festival of Lights during Thanksgiving break, which I did foolishly, right? You're gonna sit there in line for 4 hours. However, your phone's gonna say you have 4 bars and you ain't gonna be able to do nothing. Because there's so much phone traffic, people trying to watch videos, FaceTime, whatever, that they're not able to get you on because you overloaded a tower. Too many people at one spot. It's phone traffic, right? It's like a traffic jam just with your phone. That happens. Organization or flow charts, which is kind of our whole point in this lesson, right? Individuals, immediate bosses, things like who's above who. I know in one job that I had, they had like all the teachers are listed here, and then the principals here, and then the superintendents, and so like who's in charge of who, right? It's like a chart of power. So those are just 4 applications and ways we can use digraphs. Same kind of idea here. All right, project digraph. Overall visual representation of all tasks and precedence, relationships, prerequisites to flow from what can be started immediately to what has to wait on others to finish. So basically it's this, and I'll leave these 2 here so we can see the same thing together. I just kind of blurted all that out at one time. So that's probably confusing. But if you were to do this as a schedule and you were, very particular about the way that you do things, and you started your day, right? And this is on the back side of your first page. And you started your day waking up, breakfast, shower, brush teeth, dress, packing school bag, and getting to school. What would you do first? Well, first you have to wake up. So you wake up, and then you've got 2 things that you're probably going to do. To you and me, you could either shower or brush your teeth. You could be in the shower while you brush your teeth, right? But you're going to do these 2 probably first, one of them first, right? So say you shower. Well, if you shower, what would you do next? If you shower, that means you might draw an arrow down to brush your teeth, right? You do that. Or then you dress. But this is just one example of a diagram. So which one do you do? Do you shower, then dress, and then leave? Do you wake up, don't shower, don't brush your teeth, don't eat breakfast, grab your bag and leave? because that's what you do, and I know some of you are guilty of that. Do you wake up, brush your teeth, grab breakfast, and leave? Or do you forget that, brush your teeth altogether, and just wake up, grab you something to eat, and leave? Forget your bag. I know that's some of you are guilty of that as well. But this is just one example. So you could draw your own example of a diagram, right? Starting your day. How are you going to start it? You got to wake up. You're going to go have breakfast, right? Maybe you then shower. Why would you eat breakfast and then shower? I don't know. Maybe you decided to do that. Would you eat breakfast and then brush your teeth? Maybe. I hope you didn't drink orange juice because that'd be probably nasty.
Good.
But
I thought that was if you brush your teeth first and then you drink orange.
It is.
either one. Either one is not pleasant, let's just say. But again, that project diagram, this is a visual representation of all the tasks in the relationship that you're probably going to get them done. Right? So what we've done is have a flow to the way that our day begins. This is the beginning of scheduling. Some things are probably going to wait. You're not going to be able to leave or get to school until before you do some of the other stuff. You can't get to school before you wake up, and some of you will argue with me about that, and whatever. If that's what you want to argue about, you're not arguing about the right thing. You probably are going to brush your teeth before you eat breakfast. Probably. Most people have a routine. Wake up, brush your teeth, then go get breakfast. Not everybody. You're probably not, you shouldn't, let me say this, you shouldn't get to school before you pack your bag. Because then you're not prepared for the day. So a prerequisite order to the way that your day is scheduled. So I want you to now think about drawing a project diagram described in the tables here.
You want us to draw, right?
Yeah, draw your own, but here is a representation of what mine can look like. Yours could look like, right? So the procedure relations. Task, you. Here's you. X goes to you. Y goes to you. You don't have to put you in the middle, but you can. X and Y go to you. V. Here's task V. Whatever V is. Maybe V's V is taking a shower. So Y goes to V. You had to wake up before you got there, right? W, task W. X goes to W. Now, notice, I've got some other points here, and then all of them else are drawn off into, whatever. You don't have to draw the rest of them. You just need to have the 5 tasks listed, X, Y, W, U, V, and then draw them in the order that they go in. You're probably starting over here, doing something, waking up, and here maybe leaving. Because that's the procedure. You're still moving forward. You begin somewhere before you do anything, and you move forward. That's the whole idea of scheduling, right? Even if your schedule is, I'm done for the day, what are you going to do? Oh, I'm going to go relax. But you're still doing something. It might not seem like you're doing anything, but you're still doing something. And then here is another one I'll let you look at. You can go ahead and stop the recording for the procedural relations here. Again, it does not have to be exactly like mine. And then you've got the 5 computer programs I'll let you do on your own if you have not already.
Miss All, can you come and learn this one?